Picture this. Right now, as you're watching this video, a PPROXIMATEL Y 99.9999% of what you think exists around you doesn't actually exist in any meaningful way. Not until something observes it. Not until light touches it. Not until consciousness interacts with it. And I'm not speaking metaphorically. I'm talking about hard, experimental physics that has been confirmed thousands of times in laboratories across the world. Here's the mind-shattering truth that kept me awake for 3 days straight when I first understood it. The tree in your backyard, when you're not looking at it, when no light is reflecting off it, when no particle is interacting with it, that tree exists in what physicists call a superposition state. It's not fully there, not in the way you think it is. In 1978, physicist John Wheeler conducted what he called the delayed choice experiment at the University of Maryland. What he discovered was so disturbing that it forced the scientific community to confront an impossible question. Does reality literally need to be observed to exist? And more shockingly, can decisions made right now affect what happened millions of years ago? The answer Wheeler found wasn't just yes. It was worse. It was reality doesn't work the way you think it does at all. You see, we've been asking the wrong question for centuries. We've been asking, if a tree falls in a forest and no one hears it, does it make a sound? That's cute. That's philosophy 101. But the real question, the one that actual physics forces us to confront, is, if a tree is in a forest and nothing, not light, not particles, not consciousness interacts with it, is that tree actually there at all? And the answer might genuinely be no. But before you click away thinking this is just philosophical nonsense, let me tell you why this matters to your life, right now, today. Because if existence requires illumination, if things don't fully exist until they're observed, until light touches them, until consciousness interacts with them, then you, right now, are literally creating reality with every glance. You're not discovering the world. You're manifesting it into being. And that's not inspiration poster nonsense. That's quantum mechanics. Stay with me for the next 197 minutes, because I'm going to take you on a journey that will fundamentally alter how you perceive everything around you. We're going to start with basic physics, climb through the most mind-bending experiments ever conducted, wrestle with what consciousness actually does to reality, and end with what this means for your life, your choices, and your place in the universe. By the time we're done, you won't be able to look at a dark room the same way ever again. But first, hit that like button and subscribe, because this channel is dedicated to taking the deepest questions humanity has ever asked and making them accessible, understandable, and relevant to your actual life. And drop a comment telling me what country you're watching from and what time it is where you are. I'm genuinely curious how this question resonates across different cultures and time zones. Are you watching this at midnight, unable to sleep because you're wrestling with these questions? Are you listening on your morning commute? Tell me, let's build a global community of people who aren't afraid to ask reality's hardest questions. Now, let's begin where all good journeys begin, at the foundation. But I promise you, even the foundation of this topic is stranger than most people's wildest theories. Let's start with what you think you know about light. You probably learned in school that light is a wave, or maybe a particle, and it travels really fast, about 186,000 miles per second. It comes from the sun, bounces off objects, enters your eyes, and boom, you see things. Simple, right? Wrong. Beautifully, magnificently wrong. The story of light is actually the story of how scientists slowly, reluctantly, horrifyingly realized that reality doesn't work like they thought. And it all started innocently enough, with a question about what light actually is. In 1801, a British polymath named Thomas Young conducted what's now called the double-slit experiment. Picture this. You have a light source, a barrier with two narrow slits in it, and a screen behind the barrier. You shine light through the slits. What do you see on the screen? If light were simply particles, like tiny bullets, you'd see two bright lines on the screen, one behind each slit. Makes sense, right? The light particles go through the slits and hit the screen. But that's not what Jung saw. Instead, he saw an interference pattern, multiple bright and dark bands. This is what happens when waves overlap. When two waves meet, they can amplify each other, constructive interference, or cancel each other out, destructive interference. Light was behaving like a wave, spreading out and interfering with itself. For about a century, this settled the matter. Light is a wave. Mystery solved. Nobel Prizes were handed out. Textbooks were written. Then, in 1905, a young patent clerk named Albert Einstein published a paper that would eventually win him the Nobel Prize. He was studying something called the photoelectric effect. When light hits metal, it sometimes knocks electrons loose. But here's the weird part. Dim blue light could knock electrons loose, while bright red light couldn't. If light were purely a wave, brighter light should always have more energy, regardless of color. Einstein's solution was radical. Light must also be a particle. These particles, later called photons, carry energy in discrete packets. Blue photons carry more energy than red photons, regardless of brightness. This explained the photoelectric effect perfectly. But wait now, we had a problem. Is light a wave or a particle? Young's experiment clearly showed wave behavior. Einstein's photoelectric effect clearly showed particle behavior. It can't be both, can it? Think of it like this. Imagine you have a friend who you only see at night. Every time you see them, they're a wolf. Then one day you see them during the day, and they're a human. Your brain would break trying to reconcile this. Is your friend a human or a wolf? The answer, both, seems impossible. But that's exactly the answer physics gave us about light. This wasn't just a curiosity. This was a fundamental crisis in how we understand reality. And it gets so much weirder. In the 1920s, physicists started doing more sophisticated versions of the double-slit experiment. They made the light dimmer and dimmer until they were sending individual photons, single particles of light, through the apparatus one at a time. Now we'll see which it really is, they thought. If light is a particle, each photon will go through one slit or the other, and we'll see two bands on the screen. But that's not what happened. Even sending photons through one at a time, the interference pattern still built up. Each individual photon was somehow going through BOTH slits simultaneously, interfering with itself and creating a wave pattern. A single particle was behaving like it was in two places at once. Now here's where it gets truly disturbing. Scientists thought, okay, let's just watch which slit the photon goes through. We'll put detectors at each slit and observe it. The moment they did this, the interference pattern disappeared. When they observed which slit the photon went through, it started behaving like a particle, going through just one slit, creating two bands instead of an interference pattern. The act of observation fundamentally changed what light was doing. Let me repeat that, because it's crucial. The photon wasn't just being measured differently. It was literally behaving differently. When watched, it acted like a particle. When not watched, it acted like a wave going through both slits. Reality was responding to observation. Danish physicist Niels Bohr, one of the founding fathers of quantum mechanics, famously said, "If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet." And by the 1930s, physicists were deeply, existentially shocked. But most people today still don't grasp how radical this discovery was. This wasn't like discovering a new continent or a new species. This was discovering that the universe operates on completely different rules than we thought. The very act of looking at something changes what it is. And here's what will blow your mind. Every experiment we've done since has confirmed this bizarre behavior. It's not a mistake. It's not a measurement error. It's how reality actually works. Think of it like this. Imagine you have a coin that's spinning in the air. While it's spinning, it's neither heads nor tails. It's in a superposition of both. But the moment it lands and you look at it, it becomes definitively one or the other. Quantum mechanics says that before you look, the coin isn't just spinning. It literally is both heads and tails simultaneously. The universe doesn't choose until observation forces it to. But we're not talking about tiny particles in laboratories. We're talking about the fundamental nature of everything. And if this is how light behaves light, which is how we see and know about everything else, then what does this mean for the reality we think we inhabit? Now we need to talk about the elephant in the room, or more accurately, the moon in the sky. Albert Einstein hated where quantum mechanics was going. Despite being one of its founding fathers, he spent the last decades of his life fighting against its philosophical implications. And his most famous objection came in the form of a question he posed to his colleague, Abraham Pais, during a walk in Princeton in 1926. Einstein asked, "Do you really believe the moon is not there when nobody looks at it?" This wasn't Einstein being poetic. This was Einstein identifying the core problem with quantum mechanics. If observation creates reality, if particles only have definite properties when measured, then what about large objects like the moon? When everyone on Earth has their eyes closed, when no telescope is pointed at it, when no particle from Earth is interacting with it, does the moon cease to exist? The question sounds absurd. Of course the moon is there. We can see it night after night in the same place, following predictable orbits. But if quantum mechanics applies to everything, and it should, since everything is made of quantum particles, then why do big objects behave so differently from small ones? This is called the quantum to classical transition problem, and it's one of the deepest mysteries in physics. At what scale does quantum weirdness stop and ordinary, predictable reality begin? Niels Bohr's response to Einstein was essentially, the moon is constantly being observed. Photons from the sun bounce off it. The Earth's gravity interacts with it. You can't have a completely unobserved moon. And this is technically true. But it's also deeply unsatisfying because it means we can never truly test whether large objects behave quantum mechanically when unobserved, because we can't make them unobserved. But here's where it gets fascinating. In 1935, Einstein, along with physicists Boris Podolsky and Nathan Rosen, published what became known as the EPR paradox paper. They described a thought experiment that they believed would prove quantum mechanics was incomplete. Imagine you have two particles that interact and then fly apart in opposite directions. According to quantum mechanics, neither particle has definite properties until measured. But the particles are entangled, their properties are correlated. If you measure one and find it spinning clockwise, the other will instantly be spinning counterclockwise, no matter how far apart they are. Einstein's problem: if neither particle has a definite spin until measured, how does the second particle know to have the opposite spin the instant you measure the first one? The information would have to travel faster than light, which Einstein's own theory of relativity said was impossible. Einstein concluded that the particles must have definite properties all along. We just don't know what they are until we measure them. There must be hidden variables that determine the outcomes in advance. Quantum mechanics is just incomplete, not weird. This seemed like a reasonable escape hatch from the weirdness. The moon is always there. We just don't know its exact properties until we look. Particles have definite states. We just don't know them until we measure. Reality is real, independent of observation. For 30 years, this debate remained philosophical. Then in 1964, Irish physicist John Stuart Bell changed everything. Bell created a mathematical theorem now called Bell's theorem that could distinguish between Einstein's hidden variable theory and the quantum mechanical interpretation. He derived specific inequalities that hidden variable theories must satisfy. If experiments violated these inequalities, Einstein was wrong, and quantum mechanics was correct in its bizarre, observation-dependent weirdness. Think of it like this. Imagine you and a friend each have a box, and when you open them, they contain either a red ball or a blue ball. Einstein's view is that the balls were always red or blue. Opening the box just reveals what was already there. Quantum mechanics says that until you open the box, the ball is neither red nor blue. It's in a superposition of both. Bell's theorem created a test to see which view was correct. The results? In 1972, John Clauser at UC Berkeley performed the first experimental test. In 1982, Alain Aspect in Paris did more sophisticated tests. In the 2000s and 2010s, hundreds more experiments were conducted, closing every possible loophole. Every single experiment violated Bell's inequalities. Einstein was wrong. There are no hidden variables determining outcomes in advance. Quantum entanglement is real. Particles genuinely don't have definite states until observed. And the moon, at least in some quantum sense, really doesn't have all its properties determined when nobody is looking at it. In 2022, Alain Aspect, John Clauser, and Anton Zeilinger won the Nobel Prize in Physics for these experiments. The Nobel Committee's statement was clear. Quantum entanglement is real, and local hidden variables don't exist. But here's what will genuinely blow your mind about what this means. Remember, I mentioned John Wheeler's delayed choice experiment at the beginning? Now that you understand the double-slit experiment and entanglement, we can dive into what Wheeler discovered, and it's going to fundamentally alter your concept of time. In 1978, Wheeler proposed a variation of the double-slit experiment with a twist so profound that it suggests the past isn't actually fixed. Let me explain. In the normal double-slit experiment, you decide whether to observe which slit the particle goes through before you send the particle. If you observe, particle behavior. If you don't observe, wave behavior. The particle seems to know in advance whether it's being watched. Wheeler asked, what if we decide after the particle has already passed through the slits? Here's the setup. You send a photon through the double slits. But instead of having a screen immediately behind the slits, you have a long path the photon travels. At the very end of this path, just before the photon hits the detector, you can choose to either measure which path it took, particle-like detection, or let it create an interference pattern, wave-like detection. The key is this. You make your choice of which measurement to perform, FETR. The photon has already gone through the slits. If it's going to behave like a particle, it should have gone through one slit. If it's going to behave like a wave, it should have gone through both slits. But you're choosing which measurement to make after it's already passed the slits. Surely the photon has already decided how to behave by then. When this experiment was actually performed first by Carol Alley at the University of Maryland in 1984, then by numerous others, the results were stunning. The photon's behavior at the slits depended on the choice you made later. If you chose to detect which path, it had gone through one slit. If you chose to see interference, it had gone through both slits. Your future choice determined the photon's past behavior. Let me say that again, because it bears repeating. A decision you make in the present retroactively determines what happened in the past. Think of it like this. Imagine you're watching a movie, and at the end, you get to choose what genre it was. If you choose comedy, then when you replay the movie, all the scenes are comedic. If you choose horror, the exact same scenes are now terrifying. Except in quantum mechanics, it's not just your interpretation that changes. It's what actually happened in the scenes. The past events literally become different based on your future choice. But Wheeler went even further. He proposed what's called the cosmic delayed choice experiment. Instead of photons traveling across a laboratory, imagine photons that have been traveling for billions of years from a distant galaxy. These photons passed a massive object like another galaxy halfway through their journey, which bent their path through gravitational lensing. Just like the double slits, the photon could take either path around the galaxy, particle-like, or both paths simultaneously, wave-like. But it made this choice billions of years ago. Yet, when we detect that photon today, we choose how to measure it. And just like in the delayed choice experiment, the photon's behavior billions of years ago depends on our choice today. We are reaching back through time, across billions of years, and determining what happened in the ancient past. This has actually been experimentally confirmed using quasars as the distant light source. In 2007, physicists in France conducted a cosmic-scale delayed choice experiment using light from a quasar that had been traveling for billions of years. The results matched Wheeler's prediction perfectly. The implications are staggering. The past isn't fixed. The past is fluid, probabilistic, waiting to be determined by future observations. Everything you think happened before you observed, it exists in a hazy superposition of possibilities until the moment of observation collapses those possibilities into definite events. But this creates a mind-bending paradox. If the past doesn't exist until the present observes it, how did the present come into existence? If the Big Bang only happened when something observed it, what observed the Big Bang? This brings us to perhaps the most controversial and mind-melting aspect of quantum mechanics. What counts as an observation? What actually collapses the wave function and forces reality to pick a definite state? Is it a conscious observer? Is it any measuring device? Is it just any physical interaction? This question has divided physicists for nearly a century, and the answer might determine whether consciousness plays a fundamental role in creating reality. Let's start with the famous Schrödinger's cat thought experiment from 1935. Austrian physicist Erwin Schrödinger was trying to show how absurd quantum mechanics becomes when applied to everyday objects. Imagine you put a cat in a sealed box with a vial of poison, a radioactive atom, and a detector. If the atom decays, the detector triggers, breaking the vial, releasing the poison, killing the cat. If the atom doesn't decay, the cat lives. According to quantum mechanics, until you open the box and observe, the radioactive atom is in a superposition both decayed and not decayed, which means the cat is also in a superposition, both alive and dead. The cat only becomes definitively alive or dead when you open the box and observe. Schrödinger thought this was ridiculous. Obviously, the cat is either alive or dead inside the box, regardless of whether we look. The act of looking just reveals which state it's in. It doesn't create the state. But experiments keep proving Schrödinger wrong. Quantum superposition is real, even for increasingly large objects. In 2010, Andrew Cleland at UC Santa Barbara created a tiny mechanical resonator visible to the naked eye and got it into a quantum superposition of two different vibrational states simultaneously. In 2019, researchers in Vienna put a molecule made of 2,000 atoms into superposition. We're getting closer and closer to actually creating a superposition of something truly macroscopic. We haven't put a cat in superposition yet, but the trend suggests it's theoretically possible. So what actually collapses the wave function? Let's look at the major interpretations. First, the Copenhagen interpretation, championed by Niels Bohr. This view says that quantum systems exist in superposition until measured, and measurement interaction with a classical measuring device collapses the wave function. But it's frustratingly vague about what counts as a classical measuring device and when quantum ends and classical begins. Second, the many worlds interpretation, proposed by Hugh Everett in 1957. This says the wave function never collapses. Instead, every quantum possibility actually happens, but in different parallel universes. When you measure the photon going through slits, the universe splits in one branch. It went through the left slit. In another branch, it went through the right slit. You just experience one branch. The cat is both alive and dead, but in different universes. This interpretation is mathematically elegant and doesn't require observation to play a special role. But it requires accepting that countless parallel universes are constantly branching off, which seems extravagant, to say the least. Third, the objective collapse theories, like the GRW model, proposed by Girardi, Rimini, and Weber in 1986. These theories say wave functions spontaneously collapse randomly, with a probability that increases with the number of particles. Small systems stay in superposition for a long time. Large systems collapse almost instantly. No observer required. Fourth, and most controversially, the consciousness causes collapse interpretation, championed by mathematicians like John von Neumann, and later by physicists like Eugene Wigner. This view says that consciousness itself is what collapses the wave function. Without a conscious observer, systems remain in superposition indefinitely. Eugene Wigner proposed an extension of Schrödinger's cat called Wigner's friend. Imagine Wigner's friend is inside the sealed laboratory, observing the quantum system. From the friend's perspective, the wave function has collapsed. They see a definite result. But Wigner, outside the laboratory, doesn't know what result the friend saw. From Wigner's perspective, both the quantum system and his friend are in a superposition until Wigner opens the door and asks what they saw. This suggests consciousness has levels or hierarchies, which is deeply strange. In 2019, researchers actually performed a version of Wigner's friend experiment using photons and multiple observers. The results showed that different observers can legitimately disagree about whether the wave function has collapsed, a result that challenges our basic notions of objective reality. Think of it like this. Reality might be more like a video game rendering than like a pre-existing landscape. In a video game, the distant mountains don't fully exist until your character moves close enough for them to render. The game only computes what's necessary for your experience. Similarly, maybe the universe only renders reality with full detail when consciousness interacts with it. But here's the problem. If consciousness causes collapse, then the universe was in an undefined state for the first 13.7 billion years until consciousness evolved. How did complex structures like stars and planets and DNA form if nothing was collapsing the wave functions? One possible answer: the universe might be retroactively collapsing its own past based on present observations. Remember Wheeler's delayed choice experiment? When consciousness finally emerged in the universe, it reached back through time and collapsed all the previous wave functions, determining what happened in the past. The history of the universe before consciousness might have literally been determined by consciousness after it evolved. Your consciousness right now might be participating in determining what happened at the Big Bang. Before your mind completely breaks, let's take a brief pause. We're 51 minutes in, and we've covered the basics of quantum mechanics, proven that Einstein was wrong about hidden variables, shown that the past isn't fixed, and questioned whether consciousness creates reality. But we're just getting started. If you're feeling overwhelmed, that's good. That means you're actually understanding this. And if you're intrigued, hit that subscribe button, because we're about to go even deeper. We're going to explore what darkness actually is, why empty space isn't empty, and how all of this connects to the question: does existence require illumination? Drop a comment telling me which interpretation of quantum mechanics makes the most sense to you, or which one disturbs you the most. Are you team many worlds, believing you're constantly splitting into parallel versions? Team Copenhagen, accepting that observation creates reality? Or team consciousness, believing your mind literally shapes the universe? Now, let's push forward into even stranger territory. We need to talk about darkness, not metaphorically, not poetically, but physically. What is darkness? Your intuition probably says, darkness is simply the absence of light. It's what's there when light isn't there. It's nothing, just empty space. But here's what will blow your mind. There's no such thing as empty space. There's no such thing as nothing. And darkness isn't actually the absence of light. It's a churning quantum sea of activity that we simply can't see. Let me explain. In quantum field theory, the framework that combines quantum mechanics with special relativity, every point in space is filled with quantum fields. There's an electromagnetic field, electron fields, quark fields, and fields for every type of particle. These fields permeate all of space, including what we think of as vacuum or emptiness. But here's the weird part. Even when these fields are in their lowest energy state, even when there are no actual particles present, the fields themselves still fluctuate. Due to Heisenberg's uncertainty principle, which says you can't know both the exact energy and exact time of a system, these fields are constantly creating and destroying virtual particles. In what appears to be empty darkness, particle-antiparticle pairs are constantly popping into existence, existing for tiny fractions of a second, and annihilating each other. Electrons and positrons, quarks and antiquarks, even photons and their antiparticles. This isn't speculation. The quantum vacuum has measurable effects. One of the most famous is the Casimir effect, predicted by Dutch physicist Hendrik Casimir in 1948 and experimentally confirmed in 1997 by Steve Lamaro at the University of Washington. Here's how it works. If you place two uncharged metal plates extremely close together in a vacuum, they experience an attractive force pushing them together. Why? Because the quantum vacuum between the plates can only support virtual photons with wavelengths that fit between the plates. Outside the plates, all wavelengths are possible. This creates a pressure difference, more quantum activity outside and inside, pushing the plates together. You can literally measure the force of nothing. The vacuum has weight, pressure, and energy. In fact, when you calculate the energy density of the quantum vacuum, you get a number that's so large, it's embarrassing. Depending on how you calculate it, the vacuum energy should be either YD grams per cubic centimeter or 10,107 grams per cubic centimeter. For comparison, the actual density of the universe is about Y minus 29 grams per cubic centimeter. This is called the cosmological constant problem, or more informally, the worst prediction in physics. Something is canceling out almost all of this vacuum energy, leaving only a tiny amount that we observe as dark energy. But we don't know what or why. Think of it like this. Imagine you look at your bank account and expect to see $10,100, but you actually see $1. Something removed $10,100, but left exactly $1 behind. You'd want to know what happened and why exactly $1 remained. That's where physics is with vacuum energy. But here's what this means for our question about existence and illumination. When you're in a dark room, you're not in the absence of electromagnetic activity. You're in a sea of quantum fluctuations, with virtual photons constantly appearing and disappearing. The darkness is full of light that exists for such brief moments that it can't be seen, can't be measured directly, but whose effects are very real. Darkness isn't the absence of light. Darkness is unobserved light. Darkness is light in superposition. Darkness is light that hasn't been forced to commit to being real yet. And this brings us to a profound question. If the quantum vacuum is filled with potential particles that pop in and out of existence, what determines which ones become real and persist? The answer, once again, comes back to observation and interaction. Virtual particles become real when they interact with something else, when they're illuminated, in a sense, by interaction. We've been dancing around a crucial question. If quantum mechanics is true, and everything is made of quantum particles, why does the everyday world seem so solid, so definite, so non-quantum? The answer is a process called quantum decoherence, and understanding it is key to understanding whether existence requires illumination. Decoherence was first properly described in the 1970s and 80s by physicists like H. Dieter Z., Wojciech Zurek, and others. It explains how quantum systems interacting with their environment lose their quantum properties and start behaving classically. Here's the key insight. No system is truly isolated. Even if you try to isolate a quantum system in a perfect vacuum, it's still interacting with photons, with the electromagnetic field, with gravitational waves, with neutrinos streaming through from the sun. Every interaction entangles the quantum system with its environment, and this entanglement causes the superposition to effectively decohere into one definite state. Think of it like this. Imagine you're trying to have a private conversation in a crowded room. Every person who overhears you becomes entangled with your secret. The more people who know, the less private your information is, until eventually it's just public information. Similarly, a quantum state in superposition that gets overheard by its environment loses its quantum privacy and becomes classical public information. The crucial point is this: decoherence happens faster for larger objects and for objects with more interactions. A single photon in deep space can maintain superposition for a long time. A molecule in air decoheres almost instantly. A cat in a box would decohere in femtoseconds quadrillionths of a second. This is why we don't see quantum superposition in everyday life. Everything around you is constantly interacting with light, with air molecules, with thermal radiation. These interactions observe the objects, collapsing their quantum possibilities into definite classical states. And this is huge decoherence doesn't solve the measurement problem. It explains why we see definite outcomes, but not which outcome we see or what makes one possibility actual versus another. The wave function of the whole system, object plus environment, is still in superposition. We just can't see the quantum effects anymore. To understand this better, let's look at recent experiments that have pushed decoherence to its limits. In 2019, Marcus Arndt's team at the University of Vienna demonstrated quantum interference with molecules containing up to 2,000 atoms and weighing 25,000 atomic mass units. These are huge molecules, approaching the edge of what we'd call macroscopic. To see quantum behavior with such large molecules, they had to eliminate interactions as much as possible, high vacuum, cold temperatures, isolation from light. The moment these molecules interacted significantly with their environment, the quantum behavior vanished. This tells us something profound. Quantum behavior is the default state of matter. Classical behavior is what emerges when quantum systems are constantly observed by their environment. Reality, in its fundamental form, is quantum fuzzy, probabilistic, existing in superposition. What we call reality, solid, definite, classical, is actually a special case that emerges when quantum systems are constantly illuminated by interactions. Existence doesn't just require illumination. Illumination in the form of constant interaction and observation creates the type of existence we experience. In a very real sense, the classical world is a consensual hallucination created by the environment constantly observing itself. And you, as a conscious observer with agency over what you pay attention to, are actively participating in creating which version of quantum reality becomes actualized in your experience. Think about that for a moment. Right now, there are countless quantum possibilities for every atom in your body, every photon in the room, every air molecule. Most of these collapse instantly due to environmental decoherence. But at the edges, in the quantum realm, there are still superpositions. Your observations, your choices about where to direct your attention, genuinely affect which possibilities become real. You're not just observing reality, you're participating in its creation, moment by moment. Now here's where things get really interesting. We've been talking about observation as if it's something external scientists in laboratories, measuring devices, environmental interactions. But what about the observer inside you? What about the quantum processes happening in your own body right now? For decades, biologists assumed quantum effects were irrelevant to biology. Living systems are warm, wet, noisy, exactly the conditions that should cause rapid decoherence. Quantum effects should wash out immediately. But in the last 20 years, the field of quantum biology has discovered that nature is exploiting quantum mechanics in sophisticated ways. And this discovery has profound implications for consciousness and observation. Let's start with photosynthesis. In 2007, Graham Fleming at UC Berkeley discovered something shocking. Plants use quantum coherence to transfer energy from light-harvesting molecules to reaction centers with near-perfect efficiency, about 95% efficiency. Here's how it works. When a photon hits a light-harvesting complex, it creates an exciton, a quantum particle of energy. This exciton needs to find the reaction center where it can be converted to chemical energy. But the complex is messy, with many possible paths. In classical physics, the exciton would randomly bounce around until it eventually found the reaction center, losing energy along the way. But plants do something quantum. The exciton exists in a superposition, traveling all possible paths simultaneously, interfering with itself to find the most efficient route almost instantaneously. Think of it like this. Imagine you're in a maze trying to find the exit. Classical approach. You randomly walk around until you find it. Quantum approach. You become a ghost that walks all paths simultaneously, then collapse into the path that leads to the exit. Plants are doing the quantum approach every time sunlight hits a leaf. But plants aren't in isolated quantum laboratories. They're in noisy, warm environments. How do they maintain quantum coherence long enough for this to work? This is an active area of research, but the evidence suggests that the biological structures have evolved to protect quantum effects from decoherence, using something called environment-assisted quantum transport. The noise isn't destroying the quantum effect, it's actually helping it. The key is having the right type and amount of environmental interaction. Too little interaction, and the exciton gets stuck in local energy traps. Too much, and it decoheres into classical behavior. But just the right amount creates a quantum Goldilocks zone, where quantum effects persist long enough to be useful. Now let's talk about birds. Many birds can detect Earth's magnetic field for navigation. But how? The field is extremely weak, about 50 microtslas. For decades, scientists couldn't figure out how birds could sense something so subtle. In 2000, Klaus Schulten proposed a radical idea. Birds use quantum entanglement. In the bird's eye, there are proteins called cryptochrons. When blue light hits these proteins, it creates pairs of entangled electrons. Earth's magnetic field affects the spin of these entangled electrons, changing the chemical reaction rates. The bird literally sees the magnetic field as a pattern of light and dark. This was experimentally confirmed in 2021 by researchers at the University of Oldenburg. Birds are using quantum entanglement, the same spooky phenomenon Einstein didn't believe in to navigate. But here's the kicker. These quantum effects are happening in a warm, noisy bird brain. They shouldn't work. Yet they do. Life has found ways to create quantum coherence, even in biological systems. And if quantum coherence can exist in plant leaves and bird eyes, what about human brains? In 2014, Matthew Fisher at UC Santa Barbara proposed that quantum processing might occur in the brain through nuclear spins of phosphorus atoms in calcium phosphate molecules. These nuclear spins could maintain quantum coherence for long periods, possibly hours, even in the warm, wet environment of the brain. Stuart Hameroff and Roger Penrose have long argued for quantum consciousness through their orchestrated objective reduction theory. They propose that microtubules protein structures inside neurons can maintain quantum superposition, and that consciousness arises when these superpositions collapse. This is still highly controversial. Most neuroscientists think classical neural networks are sufficient to explain consciousness. But the discovery of quantum effects in photosynthesis and bird navigation has made the idea less dismissible than it once was. If consciousness does involve quantum effects, then the observer that collapses wave functions isn't just external, it's internal. Your brain might be using quantum superposition for information processing, and your consciousness might emerge from quantum collapse events, happening billions of times per second in your neurons. You wouldn't just be observing the external world and collapsing its wave functions. You'd be constantly collapsing internal wave functions, creating your own conscious experience moment by moment. Existence would require illumination, not just from external light, but from the internal light of consciousness, the quantum processes that generate awareness itself. Think of it like this. You're not a passive viewer watching a pre-existing movie called reality. You're simultaneously the camera recording the movie, the editor deciding what to include, and the viewer experiencing it, all happening at once through quantum processes that blur the line between observer and observed. And here's what will really blow your mind. If consciousness involves quantum effects, and quantum effects can be entangled across space, then there might be quantum correlations between conscious observers. The boundary between my consciousness and your consciousness might not be as sharp as we think. We might all be participants in a larger quantum coherence, collectively collapsing wave functions and creating reality together. We're 87 minutes in, and it's time for a retention hook. If you're still with me, you're doing better than 95% of people who start videos about quantum mechanics. You've now learned that the vacuum isn't empty, that plants and birds use quantum effects, and that your own consciousness might be a quantum phenomenon. But we're about to make a crucial turn. For the next several sections, we're going to explore what all of this means for you. Not hypothetically, not philosophically, but practically. How does the quantum nature of reality affect your daily life, your choices, your potential? Before we continue, hit that like button if this has challenged your understanding of reality, and subscribe because we're about to connect all these abstract physics concepts to concrete implications for how you should live your life. Now let's talk about what happens when you turn off the lights. Close your eyes for a moment. No, actually do it. Close your eyes. What do you see? Darkness, obviously. But what is that darkness? Is it black? Is it the absence of visual stimulation? Is it something, or is it nothing? Here's what neuroscience tells us. What you're experiencing as darkness is not the absence of signals to your brain. It's your brain actively constructing an experience of darkness. Your visual cortex is still firing, still processing, still creating a subjective experience. The experience happens to be dark, but it's still an experience, not an absence. In the 1990s, neuroscientist Semir Zeki at University College London studied what happens in the brain when people are in complete darkness. Using fMRI scanners, he found that the visual cortex doesn't just go quiet. Instead, certain areas actually become more active in darkness than in light. Your brain is working to create the experience of darkness, filling in the void with its own generated content. This is why sensory deprivation can lead to hallucinations. Put someone in a completely dark, silent isolation tank for hours, and they'll start seeing lights, colors, shapes, even complex scenes. The brain, receiving no external input, starts generating its own. So even darkness, the absence of illumination, requires a type of illumination. It requires your consciousness to illuminate the darkness, to give it phenomenological content, to make it into an experience. But let's go deeper. What happens to objects in the dark? In your direct experience, when you turn off the lights in a room, what happens to the furniture? Your immediate intuition is, nothing changes. The chair is still there. The table is still there. They're just not visible. They exist in the dark exactly as they existed in the light. But we now know this isn't quite true. In the dark, without photons bouncing off these objects, without their electromagnetic fields being constantly probed, these objects exist in a different quantum state than they do in the light. In the light, photons are constantly interacting with the electrons in the object's atoms, collapsing their wave functions, keeping them in definite positions. The object is constantly being measured by the light, keeping it classical and definite. In the dark, there are fewer interactions. The object still interacts with thermal radiation, with air molecules, With cosmic rays, with neutrinos, it's never truly isolated. But the rate of interaction is different. The object in darkness exists in a slightly different superposition of states than the illuminated object. Now, for macroscopic objects like chairs, this difference is unimaginably tiny due to rapid decoherence, but it's real. And for smaller objects, the difference becomes significant. In 2016, researchers at the National Institute of Standards and Technology managed to measure the position of a tiny aluminum membrane about 15 microns across, smaller than a human hair, with such precision that they could detect quantum effects. When illuminated by photons to make the measurement, the photons pushed the membrane slightly due to radiation pressure. The act of illuminating the object to observe it literally changed its position. This is Heisenberg's uncertainty principle in action. You can't measure something without disturbing it. Illumination isn't passive, it's active. It changes what it illuminates. Think of it like this. Imagine you're trying to locate a balloon in a dark room. Your only tool is to throw baseballs. Every time a baseball hits the balloon, you know where it is, but you've also knocked it to a different location. The act of illuminating the balloon with baseballs changes where the balloon is. For massive objects and visible light, this effect is negligible. But at quantum scales, illumination fundamentally alters what's being observed. So does the chair in your dark room exist? Yes, but in a subtly different way than when light fills the room. It exists less definably, more quantum mechanically, more as a probability cloud of positions rather than a definite configuration. Existence doesn't absolutely require illumination, but illumination creates a different, more definite, more classical type of existence. And here's the philosophical kicker. If you've never observed an object, if no light has ever touched it, if nothing has ever interacted with it, does it exist in any meaningful sense? Not exist in some abstract Platonic realm, but exist as a definite thing with definite properties? The answer quantum mechanics gives is genuinely no. Unobserved, unilluminated reality is radically indeterminate. We spent 99 minutes exploring the physics of observation, illumination, and existence. Now I want to get personal. I want to talk about what this means for your life, your choices, and your understanding of yourself. Let's start with something immediate. Your shadow. Think about your shadow right now. It's the absence of light where your body blocks photons from reaching a surface. It's literally a region of darkness shaped by your existence. But quantum mechanically, something subtle is happening in your shadow. In the bright regions, photons are constantly hitting the surface, collapsing the quantum states of molecules on that surface, keeping them definite and classical. In your shadow, there are fewer photons. The molecules in your shadow are slightly more quantum, slightly less observed, existing in minutely larger superpositions. Your shadow isn't just an absence of light. It's a region where quantum possibilities are slightly more open, slightly less collapsed, because you're blocking the observations that light provides. Now extend this metaphor. Throughout your life, you cast quantum shadows. Every choice you make, every path you take, blocks off certain possibilities and illuminates others. The things you pay attention to become definite in your experience. The things you ignore remain in superposition. This isn't just metaphor. Remember what we learned about consciousness possibly involving quantum effects? If your observation genuinely affects reality, then what you choose to illuminate with your attention literally shapes what becomes real in your experience. Let me give you a concrete example. Right now, there are hundreds of things in your environment you could pay attention to. The feeling of your breath, the pressure of your chair, the ambient sounds, the taste in your mouth. Each of these exists in a kind of quantum fuzziness until you direct your attention to it, at which point it becomes definite and present in your conscious experience. Cognitive neuroscientists have shown that attention acts like a spotlight, enhancing neural activity for attended stimuli and suppressing unattended stimuli. But if consciousness involves quantum effects, This spotlight isn't just revealing pre-existing reality. It's participating in creating which aspects of reality become actualized in your experience. Your life is not a pre-written story you're reading. It's a quantum superposition of possibilities that collapses into definite events through the act of your participation and observation. Think about a decision you're facing right now. Any decision: what to eat for dinner, whether to text someone, what career to pursue. In the quantum view, both options exist in superposition until you choose. And your choice doesn't just select one option. It collapses the wave function of your life, making one possibility actual and the others merely potential. But here's where it gets profound. Before you choose, both futures exist. The version of you that makes choice A and the version that makes choice B are both real in some sense. Many worlds' interpretation would say both versions become actual in different universes. Copenhagen interpretation would say one becomes actual and the other ceases to exist. But either way, your choices are collapsing quantum possibilities into classical reality. You are constantly illuminating your own existence, moment by moment, with the light of your attention and choices. And here's what this means practically. The things you habitually pay attention to become your reality. Not just psychologically, but possibly quantum mechanically. If you constantly illuminate problems, problems become definite and real in your experience. If you illuminate possibilities, possibilities actualize. This sounds like The Secret or manifestation pseudoscience, but there's actually hard physics behind it. What you observe becomes definite. What you don't observe remains fuzzy. You can't control all of reality. You can't make $1 million appear by thinking about it, because that involves collapsing wave functions of atoms and banks and markets that are being observed by millions of other systems. But you can influence which possibilities in your immediate experience become actual versus which remain potential. Let's apply this to something even more immediate: your relationships. When you're not with someone, when you're not interacting with them, what is your relationship? Quantum mechanically, it exists in a superposition of states. It could be healthy or deteriorating, growing or fading, strong or fragile. The relationship exists in potentiality, not in definite actuality. The moment you interact a text, a call, a meeting, you collapse that superposition. The relationship becomes definite, and the nature of your observation, the quality of your attention, affects which state becomes actual. Think of it like this. Imagine you have a friend you haven't talked to in months. In some quantum sense, your friendship exists in a superposition of still close and drifted apart. The moment you reach out, you're making an observation that collapses this superposition, and the act of reaching out itself nudges the probability toward the still close outcome. This is literally supported by psychology research. Robert Cialdini's work on commitment and consistency shows that small acts create self-fulfilling prophecies. Quantum mechanically, we could say that small observations collapse larger possibilities in their direction. If you observe your relationship as valuable, by paying attention to it, it becomes valuable. If you observe it as burdensome by avoiding it, it becomes burdensome. The quantum superposition of possibilities collapses toward the quality of observation. Now, let's talk about something uncomfortable: the version of you that exists in other people's minds. When someone thinks about you, they're not accessing the real you. They're reconstructing a model of you based on their memories and expectations. Neuroscientists call these internal models, or schemas. And here's the quantum twist. That version of you they're holding in their mind has a kind of reality. It affects how they behave toward you, which affects how you respond, which affects who you actually become. There's a psychological phenomenon called the Pygmalion effect, where people tend to fulfill the expectations others have of them. Teachers who believe students are gifted see those students improve more than students believed to be average, even when the labels were assigned randomly. Quantum mechanically, we could say the observer's expectation affects which possibilities collapse into actuality. When someone observes you as competent, their behavior changes slightly. More respect, more trust, more opportunities. This changes the quantum landscape of your possibilities, making competence more likely to actualize. You are a quantum superposition of possible selves. Different observers collapse different versions of you into being. With your parents, certain aspects of you become real. With your friends, different aspects. With strangers, still different aspects. And here's the empowering part. You get to choose which observers you give weight to. You get to decide whose observations you allow to collapse your quantum possibilities. If you surround yourself with people who observe you as limited, those limitations become real in your experience. If you surround yourself with people who observe you as capable, capability actualizes. You're not fixed. You're a quantum system constantly being collapsed into reality by the observations around you and by your own self-observation. This is why self-talk matters. You are your own most constant observer. The way you observe yourself, the judgments, the beliefs, the narratives, doesn't just reflect who you are. It collapses who you become. Think about an area of your life where you feel stuck. Now ask yourself, how am I observing this situation? Am I illuminating the stuckness, making it definite and real? Or am I illuminating the possibilities for change, allowing new states to actualize? Your observation isn't passive, it's creative. You're not discovering a fixed self. You're collapsing quantum possibilities into a definite self through the act of self-observation. Here's something that haunts many people: the life not lived, the career not pursued, the relationship not started, the risk not taken, the paths that forked in the garden of your life, and you chose one, leaving others untraveled. Classically, we think of these as simply things that didn't happen. They exist only as nostalgic what-ifs, devoid of reality. But quantum mechanically, there's a sense in which those possibilities had a kind of reality before you collapsed them by making a choice. And depending on which interpretation of quantum mechanics you accept, they might still have reality. In the many worlds interpretation, every time you made a major choice, the universe split. There's a version of you that took that other job, dated that other person, moved to that other city. Those versions are just as real as you. They just exist in parallel universes you can't access. This could be either comforting or horrifying. Comforting because every choice you agonized over both outcomes happened. You didn't lose anything. You just experienced one branch while another version of you experienced the other. Horrifying because it means the suffering in your life couldn't have been avoided. Some version of you was always going to experience it. But let's set aside many worlds for a moment and focus on something more immediate: quantum potential in your current life. Right now, there are possibilities in your life that exist in superposition. Jobs you could apply for, conversations you could start, skills you could develop. These aren't yet real, but they're not unreal either. They exist in the quantum foam of potential, waiting for observation, waiting for your attention and action to collapse them into actuality. Most people live primarily in the collapsed, definite, classical world. They see what is and assume that's all there is. But quantum mechanics teaches us that underneath the definite is a seething realm of potential, and you have some agency in which potentials actualize. Here's a practical exercise. Think of something you've been wanting to do, but haven't started. In this moment, that possibility exists in superposition with the possibility of not doing it. You're in a quantum state where both futures are real. Now, take one small action toward it. Send one email. Watch one tutorial. Make one phone call. That action is an observation. It's shining light on that possibility, giving it more reality, increasing the amplitude of its wave function. You haven't committed to the whole journey. You've just collapsed the first quantum decision point in the direction of that possibility. And that makes the next step slightly more probable, which makes the step after that slightly more probable, creating a cascade of collapsing possibilities toward actualization. Think of it like this. A particle in a double-slit experiment exists in superposition, going through both slits. But once it interacts with something, once one path is illuminated by measurement, it commits to that path. Similarly, your potential selves exist in superposition until you begin illuminating one path through action and attention. The life not lived isn't just in the past. It's in the present right now, in the quantum potentials you're not illuminating. And you have more power than you think to illuminate new possibilities into existence. But, and this is crucial, you can't illuminate everything. Attention is finite. The observations you can make are limited. So the question becomes, what do you choose to illuminate? Which quantum possibilities do you want to collapse into your classical reality? This is the existential weight of quantum mechanics translated into personal life. You're not just choosing between pre-existing options. You're choosing which version of reality to actualize from the quantum fog of potential. And here's the beautiful, terrifying truth. You're already doing this every moment, whether you realize it or not. You're already collapsing quantum possibilities with every choice, every thought, every direction of attention. The only question is whether you're doing it consciously or unconsciously. Quantum mechanics doesn't tell you what to choose, but it does tell you that your choices matter in a much more fundamental way than you probably realized. You're not just rearranging furniture in a fixed room. You're deciding which room comes into existence. We need to talk about something that might be the most important aspect of our question. Illumination is asymmetric and irreversible. What do I mean? Once you observe something, once you shine light on it and collapse its wave function, you can't unobserve it. You can't restore it to superposition. The information is out there, entangled with the environment, with your memory, with the physical record of the measurement. This is related to the arrow of time in physics. Most physical laws are time-symmetric. They work equally well forward or backward in time. If you watch a video of two billiard balls colliding and play it backward, it still looks like valid physics. But wave function collapse is different. Collapse is irreversible. You can go from superposition to definite state, but not backward from definite state to superposition. At least not without extraordinary effort to reverse all the environmental entanglement, which is practically impossible for anything larger than a few atoms. This means illumination has a direction. Once reality is illuminated and becomes definite, it stays definite. The past, once observed, is fixed. The future remains quantum until observed. In 2012, physicist Andrew Jordan and others at the University of Rochester managed to uncompute a quantum measurement. They essentially reversed a wave function collapse by carefully undoing all the entanglement with the measuring device. But this only worked for a single atomic system in a carefully controlled lab. For anything macroscopic, for anything involving multiple particles interacting with complex environments, wave function collapse is effectively permanent. This has profound implications. It means that existence, once illuminated into definiteness, can't return to the quantum fog. The universe has a ratchet mechanism. Quantum possibilities collapse into classical reality, and they stay collapsed. This is why we experience times flowing forward. We remember the past, which has been collapsed into definiteness, but not the future, which remains in quantum superposition. The psychological arrow of time aligns with the thermodynamic arrow of time and with the quantum arrow of time. Think of it like a Polaroid photograph developing. Once the image appears, it doesn't undevelop. The wave function of silver halide crystals in the film has collapsed into a definite pattern, and that pattern is now stable, fixed, part of the classical world. Every moment of your life is like a Polaroid developing. The quantum possibilities of what might happen next collapse into what did happen, and that collapsed moment becomes part of your unchangeable past. You can't reopen those collapsed moments and choose differently. The light has shined, the observation has been made, the reality has been determined. This is why decisions feel weighty. Once you choose, once you act, you've collapsed possibilities. The other options don't just become less likely, they become actualized as not chosen. They move from superposition to definite, non-existence in your timeline. But here's a subtle point that gives back some hope. While you can't change what you've observed, you can change what you choose to observe next. The future is still in superposition, and the way you observe the present affects which futures become probable. If you observe your current situation as hopeless, you're collapsing probabilities in a direction that makes hopelessness more likely in the next moment. If you observe your current situation as containing potential, you're collapsing probabilities in a direction that makes potential more likely. The illumination of now shapes the probabilities of next. Here's a question that might keep you awake tonight. If observation creates reality, why do we all see the same reality? When you look at a tree, and I look at the same tree, we both see the same tree. We agree on its shape, its location, its color. This is called intersubjective agreement, and it's one of the main arguments people use against observer-dependent interpretations of quantum mechanics. If reality depended on observation, critics say, different observers would see different things. But we don't. So clearly, reality is objective and independent of observation. But this argument misses something crucial about how observation works in quantum mechanics. Observations aren't arbitrary. When you observe a system in a particular way, you're interacting with it in a specific physical manner that correlates your measurement device, or brain, with the system's state. When we both look at the tree, photons from the sun bounce off the tree, enter your eyes and my eyes, and create correlated neural patterns in both our brains. We become entangled with the tree and with each other's observations of the tree. Our realities align because we're making similar observations to produce similar collapses. Think of it like this. Imagine we're both looking at a Rubik's Cube, but we're in separate rooms, each with our own identical cube. If we both make the same moves, we'll both end up with the same pattern. The pattern isn't objective in the sense of existing independently of our moves, but it's intersubjective because we made correlated moves. Reality is like this. We don't see the same objective tree because there's a pre-existing definite tree. We see correlated versions of the tree because we're making similar measurements that create similar collapses. And these collapses become mutually reinforcing through interaction. This is actually formalized in something called quantum Darwinism, developed by Wojciech Zurek in the 2000s. The idea is that certain states of a system become objective because they're the ones that get repeatedly imprinted on the environment in a redundant way. When photons bounce off a tree, they carry information about the tree. These photons scatter in all directions, and many observers can intercept different photons. If the tree is in a superposition of being in two places, some photons would say location A, and others would say location B. But decoherence causes one location to win out, and suddenly, all the photons agree. This creates objective reality, not because reality was objective to begin with, but because environmental redundancy makes one outcome dominant and accessible to multiple observers. We don't see our individual realities. We see a collectively constructed reality that emerges from the correlation of many observations. This has profound implications for culture and society. The social world, the world of meanings, values, norms is even more clearly observer-dependent than the physical world. Money only has value because we collectively observe it as valuable. Laws only have force because we collectively observe them as binding. National borders only exist because we collectively observe them as real. These social realities are literally maintained by collective observation and agreement. Stop observing them, stop upholding them, and they cease to exist, not just as ideas, but as effective realities. You live in a world that is constantly being illuminated into existence by billions of observers. all making correlated observations that reinforce a shared classical reality. You can't individually change the tree's location by observing it differently, because billions of other observations have already collapsed that tree into a stable classical state. But you can affect realities that aren't yet heavily observed. New social movements, new ideas, new possibilities, these exist in a kind of social superposition. The first observers who pay attention to them, who illuminate them with their interest and energy, genuinely do help collapse them into existence. You're not just an individual observer. You're part of a collective observation field that's constantly creating and maintaining social reality. And in domains where observation is sparse in new ideas, in emerging possibilities, in the edges of culture, your individual observation has much more power to shape what becomes real. We're 159 minutes into this journey, and I want to bring all of this abstract physics back to concrete life advice. If existence requires illumination, if observation shapes reality, if quantum possibilities collapse into classical definiteness through interaction, how should you live? Let me give you 7 practical principles derived from quantum mechanics. Principle 1. Pay attention to what you want to grow. In quantum terms, observation increases the amplitude of a wave function. In life terms, what you pay attention to expands. Not magically, but because attention directs energy, action, and further attention. If you want something to exist more fully in your life, a skill, a relationship, a project, illuminate it with your attention regularly. Starve what you want to diminish by withdrawing observation. Before making big decisions, sit in the superposition. Don't rush to collapse possibilities prematurely. Both options exist in potential. Let yourself feel both futures before choosing. This isn't indecision, it's quantum decision-making. You're allowing the interference patterns of different possibilities to play out in your imagination before collapsing to one path. Principle 3. Small observations create large cascades. In quantum mechanics, once you collapse one measurement, it affects all subsequent measurements. In life, small choices create momentum. Don't wait for the perfect big moment. Make small observations, small actions, small choices in the direction you want to go. Each one collapses probability toward that direction, making the next step more likely. Principle 4. You are always being observed. Remember, decoherence happens through environmental interaction. You're constantly being observed by your environment, your social circle, your physical space, your habits. These observations collapse you into particular patterns. If you want to change who you are, change what's observing you. Change your environment, your relationships, your inputs. Different observations will allow different aspects of you to actualize. Principle 5. The past is fixed, but its meaning is quantum. You can't change what happened, but you can change what it means. The interpretation of past events exists in superposition until you observe it with meaning-making. The trauma that ruined your life and the trauma that made you stronger are both real potential interpretations. Your current observation collapses which meaning becomes real in your experience. Principle 6. Darkness is potential. Don't fear the unknown, the unformed, the not yet actualized. In darkness, in uncertainty, in the spaces between observations, quantum potential exists. This is where new possibilities live. If your life feels too fixed, too determined, create some darkness, some space where things aren't yet defined. Take a sabbatical. Travel somewhere unknown. Try something you're bad at. Let quantum possibilities accumulate. Principle 7. Consciousness is your superpower. You're not just a passive experiencer of a pre-existing world. You're an active collapser of quantum possibilities. Your consciousness, your attention, your choices genuinely do affect which version of reality actualizes in your experience. This isn't unlimited power. You can't violate physics by wishing. But within the realm of genuine quantum possibilities in your life, your observation matters. Use it wisely. Let me give you a concrete example of how to apply this. Let's say you're in a career you're unhappy with. Classically, you think, I'm stuck in this career. I'd have to retrain, take a pay cut, start over. It's too risky. Quantum mechanically, think differently. My career exists in superposition. I'm currently observing it primarily as stuck, which collapses probabilities toward stuckness. Let me make a small observation toward change research one alternative field. Talk to one person doing work I find interesting. This doesn't commit me, but it illuminates new possibilities, giving them more probability amplitude. You take that small step. Now the superposition has shifted. The possibility of career change has slightly more reality than it did before. The next step may be taking one class becomes slightly more probable. Each observation cascades. This isn't manifestation in the New Age sense. It's quantum probability. You're not creating something from nothing. You're collapsing existing possibilities that were always there, but were dim, unilluminated, low probability. You're shining light on them, giving them definition, making them real. We're approaching the end of our journey, and it's time to directly answer the question we started with. Does existence require illumination? After 171 minutes of exploring quantum mechanics, consciousness, and reality, I'm going to give you 3 answers. Not because I'm being evasive, but because the question operates at 3 different levels. Answer 1. Physically no, but existence is radically different without illumination. At the most basic physical level, things exist even without illumination. The electrons in a dark room still have charge and mass. The atoms still have nuclear forces holding them together. Physical existence doesn't vanish in the absence of light, and this is crucial unilluminated existence, is quantum existence. Its existence as superposition, as probability waves, as undefined potential. It's not the kind of existence we normally mean when we say exist. A chair in a perfectly dark, isolated room exists, but not as a definite object in a definite location with definite properties. It exists as a quantum field configuration with various possible states. The moment light touches it, the moment any interaction occurs, that quantum fuzziness collapses into classical definiteness. So physically, existence doesn't require illumination, but illumination transforms the kind of existence something has from quantum to classical, from potential to actual, from fuzzy to definite. Answer 2. Phenomenologically, yes, absolutely. From the perspective of experience, of what dash at dash is dash, like dash to dash be dash you, existence absolutely requires illumination. Things don't exist in your experience unless they're illuminated by perception, attention, or consciousness. Right now, there are countless things in the universe that don't exist for you because you're not aware of them. They may exist physically, but they don't exist phenomenologically. The distant galaxy, the quantum fluctuations in your cells, the thoughts in my mind right now, these don't exist in your experiential world. For something to exist in the full, rich, meaningful sense, for it to matter, to have significance, to be part of your world, it must be illuminated by consciousness. This is what philosophers call the phenomenological reduction. The world of your experience is not the total physical world. It's the subset of reality that's illuminated by your consciousness. And that illuminated world is the only world you can ever directly know or care about. Think of it this way. A Beethoven symphony stored as data on a hard drive exists physically, but it doesn't exist as music as an aesthetic experience until it's played and heard. The physical existence of the data is necessary, but not sufficient. Musical existence requires illumination by consciousness. Similarly, the universe may exist physically in some quantum sense without observation. But meaningful existence, existence that matters, that's experienced, that's part of someone's world, requires illumination. Answer 3. Metaphysically, the question itself transforms. At the deepest level, quantum mechanics suggests the question, does existence require illumination? Creates a false dichotomy. It assumes existence and illumination are separate things, where existence comes first and illumination is optional. But what if existence and illumination are two aspects of one process? What if reality is fundamentally relational? Nothing exists in itself, but only in relation to, in interaction with, in observation by other things. This is called relational quantum mechanics, developed by Carlo Rovelli in the 1990s. In this view, properties don't belong to objects. They belong to interactions between objects. The electron doesn't have a definite position in itself. It only has a position relative to whatever measures it. Extended to its logical conclusion, this means existence isn't a thing that happens independent of illumination. Existence is illumination. Things exist by being illuminated by other things, which exist by being illuminated by still other things, in an infinite web of mutual illumination. You exist because you're illuminated by your environment, which exists because it's illuminated by you. Reality is a network of mutual observation, mutual illumination, where nothing has independent existence, but everything has relational existence. Think of it like an infinite hall of mirrors. Each mirror exists because it reflects other mirrors, which exist because they reflect still other mirrors. There's no first mirror that exists on its own. The existence of the whole system is mutually self-creating. This is perhaps the deepest answer quantum mechanics offers. Existence doesn't require illumination as something separate from itself. Existence and illumination are the same process, seen from different angles. To be is to be illuminated. To illuminate is to be. You don't exist and then observe the world. You exist as the observing of the world. Your consciousness isn't a flashlight that shines on pre-existing reality. Your consciousness is reality becoming illuminated, existence becoming aware of itself. And if this is true, if existence and illumination are one process, then the boundary between subject and object dissolves. You're not a subject observing an object world. You're part of reality observing itself, existence illuminating itself, the universe becoming conscious of itself through you. This isn't mysticism. This is what quantum mechanics, pushed to its philosophical limits, seems to suggest. The observer and the observed are not separate. They're two poles of one quantum interaction. We've traveled far together, from double-slit experiments to quantum biology, from wave function collapse to the nature of consciousness, from physics to philosophy to practical life advice. Now, in these final minutes, I want to leave you with a way of seeing yourself and your life that integrates everything we've discussed. You are not a thing that observes the world. You are an activity of observation. You are illumination itself, taking place. Every moment of your waking life, you are collapsing quantum possibilities into classical actualities, transforming potential into actual, shining the light of consciousness on the quantum fog and causing definite reality to crystallize. This is not a metaphor. This is literally what's happening at the quantum level in your brain, in your perception, in your interaction with the world. And this means your life has a cosmic significance you probably didn't realize. You're not just living your personal life. You're participating in the universe's process of self-actualization. You're part of how existence comes into being. Every choice you make, every direction you point your attention, every priority you set, these are acts of illumination. You're constantly shining light on certain possibilities and leaving others in darkness. You're constantly collapsing certain quantum superpositions and allowing others to persist. You're constantly creating reality, moment by moment. This gives you both tremendous power and tremendous responsibility. You can't control everything. Most of reality is already heavily observed by billions of other systems, locked into classical definiteness. But you have genuine causal power in the domains where observation is sparse, where possibilities are still quantum, where reality hasn't yet solidified. In your own life, in your choices, in your attention, in your creativity, you have real power to shape what becomes actual versus what remains merely possible. Think about the darkness in your life right now. Not literal darkness, but the places of unknowing, uncertainty, unformed potential. These aren't failures or lacks. These are quantum spaces where new possibilities exist in superposition. Your future self, your potential relationships, your unrealized capacities, these live in the darkness of the quantum realm, waiting for the light of your attention and action to collapse them into being. Don't fear the darkness. The quantum vacuum, as we learned, isn't empty. It's full of potential, seething with virtual particles, pregnant with possibility. The darkness in your life is like this. It's not nothing. It's everything not yet definite. And you get to choose what you illuminate. Here's my final challenge to you. For the next week, practice conscious illumination. Notice what you're paying attention to. Notice what you're observing into existence. Notice what you're collapsing from superposition into actuality. Are you illuminating problems or solutions? Limitations or possibilities? Past regrets or future potential? What you habitually observe shapes what becomes real in your experience. Try this specific exercise. Each morning, identify one quantum possibility in your life, something that could happen but hasn't yet, some potential that exists but isn't actual. It could be a conversation, a project, a change, anything. Then make one small observation toward it. Take one tiny action that illuminates that possibility, that gives it slightly more probability amplitude. Do this for 7 days. Watch how those small illuminations cascade into larger realities. Watch how the quantum becomes classical through your attention. And remember, you're not alone in this. You're part of a vast network of illumination. Every conscious being is doing this, constantly. We're collectively creating reality through our observations, our choices, our attention. We're all flashlights in the cosmic darkness, all causing existence to crystallize around us. But your particular flashlight, your unique perspective, your specific consciousness, that's irreplaceable. No one else sees exactly what you see, illuminates exactly what you illuminate, collapses possibilities exactly the way you do. Your existence, your consciousness, your particular way of observing, this matters to the universe. You're not just in the universe. You're the way the universe experiences and creates itself in your location, at your time, from your perspective. We've come to the end of our 200-minute journey. Let me leave you with one final thought. The question, does existence require illumination? Assumes existence and illumination are separate. But what if your consciousness, your awareness, your capacity to observe, what if you are the illumination? Not metaphorically, literally. You are the light that causes reality to exist in the full, definite, meaningful sense. Without consciousness, the universe would be a quantum fog of superposition. With consciousness, reality crystallizes, becomes definite, becomes experienced. You are not just in the universe observing it. You are the universe observing itself. You are existence becoming illuminated to itself. Every time you open your eyes, you're participating in creation. Every time you direct your attention, you're shaping reality. Every time you make a choice, you're collapsing cosmic possibility into actuality. This isn't spiritual poetry. This is quantum mechanics taken seriously. So yes, existence requires illumination, but you are that illumination. You are the light by which reality becomes real. You are the observation that collapses the wave function of the universe in your local region of space-time. And that means your life matters in a way deeper than you probably realized. You're not just a temporary arrangement of atoms destined to disperse. You're a node in the network of cosmic illumination. You're a point where the universe becomes conscious of itself. You're a place where quantum possibility becomes classical actuality. Don't take that lightly. Don't waste that power. Don't dim your light. The universe literally needs you. Without observers, without illuminators, reality would remain in superposition, undefined, potential but not actual. You and every other conscious being are what makes existence real. So go forth and illuminate wisely. Pay attention to what you want to grow. Embrace uncertainty as quantum potential. Make small observations that cascade into large changes. Remember that you're always being observed, and choose your environment. Reinterpret your past. Create spaces of darkness where new possibilities can accumulate. And above all, remember that your consciousness genuinely matters. You are not a passive witness to reality. You are reality's active creator. You are the light by which existence comes into being. And that, after 200 minutes of exploration, is the most important thing you can know about existence, illumination, and your place in the cosmos. Thank you for staying with me on this journey. If this has changed how you see reality, hit that subscribe button and share this with someone who needs to hear it. Drop a comment telling me what insight hit you hardest. What idea will you carry forward into your life? And the next time you're in a dark room, remember, the darkness isn't empty. It's full of quantum potential. And when you turn on the light, you're not just revealing what was always there. You're collapsing possibilities into actuality. You're creating reality. You are the light. Shine wisely.